Hey everyone, this video is on matrix operations. So operations with matrices. Now this is useful if you're going to take a linear algebra class. Many people take linear algebra if you're in a computer science major, engineering of course, math, even a lot of sciences, chemistry, biology. Okay, so let's start talking about it. A matrix of m rows and n columns is called a matrix with dimension m by n. So that x in the middle, we use the word by, not times, m by n. Okay, so here's some examples. So you always read the rows first and the columns second. So how many rows does this first one have? It has 2 rows. How many columns? 3 columns. So this would be a 2 by 3. How about the second one? How many rows? 3 rows. How many columns? 3 columns. 3 by 3. Number 3, how many rows? 2 rows. How many columns? 1 column, 2 by 1. Last one, how many rows? 1 row. How many columns? 2 columns. That's a 1 by 2. So that's just how you would name them. Okay, the numbers in the matrix are its elements. So they're called elements. Each number is called an element. 2 matrices are equal if their dimensions are the same and the elements in the corresponding positions are equal. Okay, so in part A here, the first matrix is 2, 3, and the second one is 2y. Since they're equal, there's already an equal sign in between, and the first elements are the same, they're both 2's, that means the second elements must be the same. So what does y have to equal? Right, y has to equal 3. In part B, we have 2 by 2 matrices. They're equal. The 7 and -1 are the same in both sides. So that must mean the other elements must be also equal. So we have 2 of them to find. What's our A and what's our B? Well, the A has to match the 5, and what does the B have to match? Right, 3. So A equals 5 and B equals 3. Part C and D, there's just a little bit of work to do. Again, this is also a 1 by 2 on both sides of the equal sign. The 6's match, so that must mean the second elements have to match. X plus 2 has to equal 7. Subtract 2 on both sides, that'll give us what x is equal to. So x equals 5. In part D, it's the same thing. The -2 and 3 match, so that must mean the 5y has to equal the -15, and the x minus 4 has to equal the 9. Go ahead and work that out. X minus 4 equals 9, so x equals 13, and 5y equals -15, so y equals -3. There are our 2 answers, 13 and -3. Okay, so now we're going to talk about adding matrices. To add matrices, we add the corresponding elements, and they must have the same dimensions. So notice I wrote four matrices. A and B are both 2 by 2 matrices. And C and D are, that's right, 2 by 3 matrices. So we have two problems to do. We're going to add the A and B. And we can do that because they're both have the same dimensions. And then we're going to add the C and D because they both have the same dimensions. All right, so let's do A plus B first. We simply add the corresponding elements. So -5 plus 6, that's in the first position. 0 plus -3 is in this top row, second column. And then 4 plus 2, that's in the bottom row, first column. And then 1 plus 3, bottom row, second column. And then simplify that, and we're all done. Okay, C plus D is very similar. Maybe you might want to pause the video and work it out. You're going to add each element, the matching elements, and keep it in the same position. So the 2 plus 4, the 5 plus -1, the -2 plus 3, etc. And then here's our final answer. Reading by rows, 6, 4, 1, 7, -13, 5. Not too bad, right? It gets a little better, I gotta be honest with you. When I mean better, I mean worse. Okay, here we go. Now we're going to talk about subtracting matrices. To subtract matrices, we subtract the corresponding elements. Again, they must have the same dimensions. So this time, instead of adding, we're simply subtracting. All right, A minus B. So it's going to be -5 minus 6. That's going to be in the first column, first position. So it's the same as the last example, but instead of adding the elements, we subtract them. Okay, then work it out. And you should get -11, 3, 2, -2. Why don't you try to pause the video and work out C minus D? Okay, same idea. 2 minus 4, 5 minus -1, -2 minus 3, 4 minus 3, -7 minus -6. Remember, a minus and negative turns into a plus. And then we work them out. -2, 6, -5, 1, -1, -5. All right, here we're going to talk about multiplying a matrix by a number. We multiply each number inside our matrix by the number. This is called scalar multiplication. So scalar just means it's a number. It doesn't have a direction. It's just a number, a simple number. All right, so 3a. So we're going to multiply 3 times a. So you could write it with a 3 in front of the matrix A. And then you multiply each one inside by 3. So that'll give us -15. 3 times 0 is still 0. 3 times 4 is 12. And 3 times 3 is, 3 times 1 is 3. So -15, 0, 12, 3. All right, -2c, why don't you give it a shot? Try to pause and work it out. You're going to multiply each one of the numbers inside by -2. All right, -4, -10, 4, -8, 14, and 0. All right, matrix multiplication. So we're talking about multiplying matrices now. The first note that we want to write down is that the order makes a difference. AB is different from BA. So multiplication with matrices is not commutative. The second note we have here is that the number of columns in the first matrix must equal the number of rows in the second matrix. In other words, the inner dimensions must be equal. I know, a little complicated, right? Okay, the answer, our third note. Now we're talking about the answer, what it's going to be. We want to know what we're going to expect. The answer will be the number of rows in the first matrix by the number of columns in the second matrix. In other words, the outside dimensions. So we're looking at these two examples here, and we want to know, first of all, is it possible? And what kind of answer can we expect? Okay, let's look at the first one. Is that a 2 by 1 or a 1 by 2? Right, it's a 2 by 1. It's 2 rows, 1 column. How about the second one? That's a 1 by 2. So going back to that second note, it says that the number of columns in the first matrix must equal the number of rows in the second matrix. Easy way to think about that is it's the inner numbers. Look at the two inner numbers that we just wrote down. We wrote down 4 numbers. The two inner ones are the two ones. Are those two numbers the same? Are they equal? Yes, that means we can do it. And then the answer is going to be the outside dimensions. So our answer is going to be the outside numbers, which will be a 2 by 2. I know it's strange, so when we multiply that, we actually get a 2 by 2. Okay, now I just reversed the order here. The first one is a 1 by 2. The second one is a 2 by 1. We can still multiply it because the inner numbers are the same. What could we expect our answer to be? Right, a 1 by 1. Interesting, right? So that just means one number, 1 row, 1 column. Yes, you're right. Math is fascinating. I concur. All right. Okay, so on this slide, all we're doing is we're just seeing if the multiplication is possible. So we want to look at our first example here. Remember, it's rows by columns. So the first matrix is 3 rows by 2 columns. The second one is also 3 rows by 2 columns. So can we do it? Are the inner dimensions the same? No, we cannot do this one because the inner numbers are different. How about our next one? Remember to pause it and work it out. See if you should only answer a yes or no on these problems. So the first one is a 2 by 3 and the second one is a 3 by 2. Are the numbers the same in the middle? Yes. All right, this one is a 3 by 2 and a 2 by 3. Are the numbers inside the middle? Yes. And then for an answer, we should get a 3 by 3. We'll talk about that more later. Okay. 3 by 1 and a 1 by 3. Can we do it? Yes. The ones are the same. Bottom row, they're both 2 by 2s. The two middle dimensions are both 2. The inner dimensions are 2, so we could do it. And this last one's a 3 by 3 and a 2 by 2, and the inner dimensions are not the same, so no, we can't do that one. Okay, so we're doing the same thing, but this time we just want to know what our final answer will be. All right, so this first one, can we even do it? No, we can't do that one, right? Cannot do. So we could not worry about that one. These are the same problems from the last slide. 2 by 3 and 3 by 2. Can we do it? Yes. And what's our answer going to be? The outer dimension, so it'll be a 2 by 2. Okay, middle row, sorry, 3 by 2 for the first one and a 2 by 3. We could do it because the inner dimensions are the same, so our answer is going to be the outer dimension, so our answer will be a 3 by 3. A 3 by 1 and a 1 by 3, yes, we could do it. And our answer is going to be the outer dimensions, which is a 3 by 3. All right, bottom row, they're both 2 by 2s. We could do it, and our answer will be a 2 by 2, the outer dimensions. And the last one, we can't do it. So no bother. So if this was a homework problem and you couldn't do it, you just don't want to say, I don't know, or leave it blank. You want to make a statement that it's not possible. So you could write not possible, cannot do, something of that nature. Okay, matrix multiplication. The product of two matrices is found by multiplying the corresponding elements in each row by each column and then adding them together. So I kind of made two little ellipses here, or two ovals. Row is on the left, column is on the right. All right, I know, probably confusing, right? But we'll do some examples. Okay, so we're going to do this operation. First of all, it's a 2 by 3 and a 3 by 2. So can we do it? Yeah, it's a 2 by 3 and a 3 by 2, so we can do it. And what should we expect our answer to be? Right, a 2 by 2. Okay, so let's do it. So remember I said, or I put some ovals on the previous slide? So what you're going to do is you're going to put a horizontal oval on the first row and a vertical oval on the first column of the second one. Now you're going to multiply each corresponding element. The first element of the first row with the first element of the first column, and then the second element of the first row, and then the second element of the column, and the third element of the row with the third element of the column. All right. So make a big matrix here. So 1 times 0, 2 times 1, and 4 times 5. First element times the first element, second element times the second element, third element times the third element. Okay, now we're going to do the second row with the first column. And then that result is going to go in the second row, first column. So last time we multiplied the first row, first column. The result is in the first row, first column. Now we're doing second row, first column. The result is going to go in the second row, first column. Okay, and then again, you multiply first element with first element, second element with second element, third element with third element. So 3 times 0, 9 times 1, 2 times 5. Okay, now we're going to do the first row again, but this time we're going to take the second column. So we're multiplying the first row with the second column. Where should that result go? It should go in the first row, second column. Again, multiply the first element with first element, second element with second element, third element with third element. 1 times 1, 2 times 4, 4 times 8. We'll work it out in the next part. Okay, now we're going to move to the second row. So now we're going to do the second row, second column. Where should the answer go? In the second row, second column. First element with first element, second element with second element, third element with third element. 3 times 1, 9 times 4, 2 times 8. And now simplify that answer, 22, 41, 19, 55. I know it takes a little getting used to, but you can do it. Okay, here's a couple of 2 by 2 matrices, and we can multiply that. Our answer is again going to be a 2 by 2. Okay, here we go. Row by column. Row, column. First row, first column. Where's the answer going to go? First row, first column. Each element by its corresponding element. First element times first element, second element times second element. There is no third element here, so that we stop there. So 4 times 2 and 2 times negative 3. Okay, now we're going to move on to the bottom row. So bottom row, first column. So our answer is going to go in the bottom row, first column. And we multiply corresponding elements. 3 times 2 and 1 times 3. Okay, now we're going to move on to the second column. First row and the second column. Our answer is going to be written in the first row, second column. So 4 times 0 and negative 2 times 5. Last one, bottom row, second column. So our answer is going to go in the bottom row, second column. And then simplify it and you're all done. Okay, this looks kind of simple, right? It's a 2 by 1 and a 1 by 2. Yeah, we could do it because the ones match and our answer is going to be a 2 by 2. Interesting, right? See how this works out. Okay, row by column. It's just kind of weird because when we take the first row, it's only one number. And when you take the first column, hey, again, it's only one number, but that's it. So in our 2 by 2, it's going to be 4 times 3. Okay, now we'll move on to the bottom row. Bottom row and first column. So that'll be 7 times 3. Now we're going to move on to the second column. So first row, second column. 4 times 5, that's it. And then move on to the second row, second column. Second row, second column, the answer will be in the second row, second column. And that's it, we're all done with this. 12, 20, 21, 35. Okay. The identity matrix. The identity matrix has ones along the diagonal and zeros everywhere else. This probably looks familiar. You might be thinking of Gauss-Jordan, and you're not far off. There's a little bit of Gauss-Jordan involved. So if you didn't like the Gauss-Jordan method for solving a system of equations, there's a little bit more. Okay. So I just wrote some notes. So ones along the diagonal, and we're only going to talk about 2 by 2s and 3 by 3s, but you could have 4 by 4s. You could have 4 rows and 4 columns. Not in this lesson or not in this video, but you could have that. So the identity matrix is denoted by the capital letter I. And any matrix multiplied by the identity matrix equals the original matrix. So whenever you multiply anything by I, you get the same thing, provided the multiplication is possible. Okay. Also, the order doesn't matter. The identity matrix could be first or last. If you multiply anything by the identity matrix, you still get the same thing. Okay, so here's an example of multiplying matrix by the identity. In this case, they're both 2 by 2s. Okay, so same thing that we were just doing. Row by column. And you multiply the corresponding elements. So 4 times 1, negative 2 times 0. And then we move on to the bottom row. The order doesn't matter. I'm just going with the bottom row in the first column. So that would be 3 times 1 and 1 times 0. And then we're going to move on to the second column. So first row and second column. That's going to go in the first row, second column. And then the last one will be second row, second column. The answer will go in the second row, second column. And when you work it out, we get the original matrix. Same thing. And that's what we expected. It wouldn't have mattered if the 1, 0, 0, 1 was first or second in this case. You would still get the same answer. Okay, last topic. The inverse of a matrix. The inverse of a matrix A is denoted by A inverse. So this notation that we use, it's kind of like an exponent. It's a -1. So that -1, you say it as A inverse. You don't say A to the -1, you say A inverse. Okay? The product of a matrix A and its inverse equals the identity matrix. So A times A inverse equals I, and A inverse times A equals I. Order doesn't matter. And remember, the identity matrix is 1, 0, 0, 1 for a 2 by 2. Or for a 3 by 3, it's ones along the diagonal and then zeros everywhere else. Any identity is always ones along the diagonal and zeros everywhere else. It could be a 4 by 4. In that case, the diagonal would have 4 ones. Okay, this is what we need to do. How to find the inverse of a matrix? Well, we've already learned the method. It's the Gauss-Jordan method. Yeah, that's right, the Gauss-Jordan. You might have learned that already. Okay, step 1. Write the augmented matrix consisting of the given matrix on the left-hand side. So we're going to make a big augmented matrix, and the given matrix that we have, that's going to be on the left. And then we're going to write the identity matrix on the right. And then we're going to use row operations to transform the matrix on the left-hand side to the identity matrix. Our answer, which will be the inverse matrix, will be on the right-hand side. Okay, so write that down. Probably doesn't make sense until we see an example, but we're going to do that right now. Okay, here's our matrix that we want to find the inverse for. We're going to put that on the left-hand side, and then we're going to put the identity on the right-hand side. So we're using Gauss-Jordan. We're trying to get ones where the 4 and negative 2 are, and then we're trying to get zeros where the negative 3 and 3 are. So first thing is we want to get a 1 where the 4 is. So we're going to multiply the bottom row by negative 1, then add it to row 1. So if you multiply negative 1 times the bottom row, you get negative 3, 2, 0, 1. Sorry, negative 3, positive 2, 0, negative 1. And the top row stays the same, and then when you add them together, we're going to get 1, negative 1, 1, negative 1. So we're going to go ahead and put that on the top row. Okay, now we want to get a 0 where the 3 is. So we're going to take our top row, multiply it by negative 3, and then add it to the bottom row. So multiply negative 3 by the top row. That gives you negative 3, 3, negative 3, 3. Add it to the bottom row. 0, 1, negative 3, 4. Where does that go? Right, that goes in the bottom. We're almost there. It's not too bad. We've got to get a 0 where the negative 1 is. Well, luckily, if we just add the two rows together, we'll get a 0 there. So that'll give us 1, 0, negative 2, 3. That's going to be our new top row. And we've done it. We've got the identity matrix on the left, and our inverse is on the right. So there's our inverse, negative 2, 3, negative 3, 4. Okay, that was the last example I'm going to do. It is a lot of work. I totally agree. And then we're at the end of this video, so you're probably getting a little exhausted of this lesson. But for a 3 by 3, it's still the same process. You're going to put the 3 by 3 on the left and the identity matrix on the right, and then you do the same thing that we did when we did Gauss-Jordan. Get ones along the diagonal on the left side and zeros everywhere else. And then the answer is going to be the 3 by 3 on the right-hand side. All right, so I kind of weaseled out on this last one. I didn't do a last problem, but you get the idea, hopefully. All right, that's it. I'll see you later.